So my name is Sergii. I'm here at Stylight, and I was building like a bit of a data warehouse, and like also like together with DK was building a bit of like data lake, right? So if you look at title, right, there's like a couple of things that we already mentioned, like data warehouse, data lake, right? But there are also like two data engineers, right? So I think it's kind of makes sense to start from there. And now you're going to be surprised because there are like a bit of more than two people on this slide. And the moment we were like, naming this title for this presentation, idea was to basically say two engineers that were working like the same time, right? Because somewhere in the beginning we had Tiago like working on that right now is in Berlin, or like Quentin was kind of like helping us, or Stefan that is like somewhere, I think somewhere in this building, yeah. But right now it's like two of us kind of like gonna tell you a couple of pieces how it was happening. Sorry, he says. Oh yeah, so there is a Stefan. Stefan from the picture, yeah. So I'm Sergii, and there is DK.
Hi, my name is Dineshkarthik Raveendran. As you know, it's big, that's why people call me as DK. It's simple to say. And I'm a data engineer in Stylight for the past 1 year, and yeah, I have been with this journey for the 1 year. Yeah.
And you can be laughing like why DK was suggesting from DK's side. It's not we said like, okay, your name is too long, so we're gonna name you differently now. It was his suggestion, so nothing like really bad about that. But you see the office that we have is kind of like big, so it's not only like those 3 plus 2 people, it's like a bit more. So this is like a bit of like Stylight crowd before we went to Oktoberfest. In the next couple of slides, I'm going to explain what is Stylight, but it's not because I would like to, telling like about how much money we are making, but more like to define like scope a bit like from there. Yeah, if you would ask like, do you know, is there anybody who doesn't know what is Stylight? Everybody's aware. Oh, one person. Okay. Look, it's totally fine. So we're trying to do this, what's written like a big letters, making style happen. So it's mostly like aggregating information from like many products in one platform, doing some machine learning, like getting information about those products and providing the most relevant ones to the users, basically. And in this platform, we have like more than 1,200 shops, basically 30 million products, just to understand for you like what scale of information from those products flying in. And we have quite a bunch of like interesting things inside. And we kind of like making lots of money, like lots of users, blah, blah, blah. It's like all not interesting. So potentially what might be interesting is that we started like around 2008, 2009, and right now it's like 2019, right? So you can imagine how much legacy stuff we have around the places, but it's also going to be related to how we were building things. And in between there were like a bunch of different countries, right, that we were like launching. So originally it was kind of like starting with like, I don't know, mostly Germany, and after adding like one more country. And you as a data engineer can understand that originally it looks like super easy. You're going to have some MySQL instance doing all the stuff just in production, and after it's getting like harder and harder to process all this data. Yeah. And that's basically growth of like number of products, right? So in the beginning was like around, I don't know, 100,000 products for entire platform, and it's gonna be like easy to collect information about those, and it ended up like being like 30 million products that you need to understand. Yeah, and if you today look at data platform, I think the data that Stefan just like pulled today is like around 15 billion rows inside of data warehouse. We have like more than 60 users using like our reports of our products like on daily basis, and like more than 300 hours that people query our data. I don't know how users can imagine this one, but it sounds like many hours of querying or waiting for queries. Hopefully not the second one. Yes, but what are the use cases? Like what are we talking about? And if you feel like it's going too fast or you kind of like getting lost, just like raise your hand and we can talk about that. Anybody getting lost? No? Okay, hopefully not. I think it's nothing really like completely new for you, right? But just like let's walk through those. So, as a data platform, especially in the case of Stylight, we originally started as kind of like, we have a couple of people and they know how to run queries, right? And let's ask all of them like questions, right? What usually defined gonna be BI as defined, right? And it's kind of like over the years transitioned in the direction of like, okay, we have a couple of people, but those people don't have enough time to answer all of your questions, right? So what if we're going to be building like products that you can be using, right? And that means that on one hand you have more technical users, somebody who is sending like, I don't know, I have some data about my partners, right? And I would like to make it available to like other team and department, right? And that's what here we are writing, like we have big files from the teams and we would like to batch import it like elsewhere, right? But there are also like many other teams that would like sometimes send like a smaller events. Maybe there is something like on a website, maybe we do some, I don't know, machine learning tagging and we would like to say, okay, this product has a tag, I don't know, shoes, and this product has a tag of, I don't know, sneakers, or was like tagged or QA'd or stuff like that. And that's what we call like smaller chunks of data or like streaming part, right? And there's also like a bunch of events as, I don't know, like any data-driven companies that you can receive from, maybe from Google because you have analytics, or maybe from Adobe because you do bidding, like, or bunch of other things. But essentially they all kind of like connected in the same direction of Lambda architecture. So nothing really crazy there. If you would look at this one, very simplified, right? At some point, it looked like something like this, right? So we have like a Redshift that I think it was kind of like our mid-journey that would have like around 4 nodes inside of the cluster. We have like a bunch of like a different ATL jobs that going to be pulling data and you know, processing them, and a bunch of like a smaller ones like inside of data streams. And on top of it, we can have like some reporting inside of like Periscope. We have some internal systems that called changelog, and some significance testing basically, so you can help our product people to understand how it's working. Although this drawing is very nice, for that is kudos to Stefan for building it amazingly. It doesn't really explain you much of details how it works internally. So here we have a bit of more details to explain a couple of pieces how it was working. So originally we started using like Snowplow. Anybody is aware what is Snowplow or heard of it? Yeah? Okay. So, sorry? Yeah, like at north, there's like lots of snows there. Yeah, from that direction, yes. So there's like open source product called Snowplow that allows you basically to have like a different pieces and components for, I don't know, like trackers, for collectors, for instance. And they also like support this part, but for us it didn't look like very flexible, so we decided to just rebuild it altogether. So if you look at this one, right, it has kind of like 2 branches, right? One branch and another one, right? One branch is more like for events that going like in streaming fashion or event-based architecture. And here you can see like we have some trackers. Mostly it's going to be like some client libraries that might send it like from, I don't know, from Android or from web or whoever else, right? You have some collectors basically that get those events and after writing to Kinesis, right? That who is not aware what is Kinesis? Everybody is so excited and knows what is Kinesis. That's good. So I'm not going to explain too much. Inside of that, we have process that basically can run on a stream of Kinesis, right? Together with the schemas of those events inside of Igloo. And after you can validate if events are good or not so good, meaning bad, right? After that, you can have some buffer that essentially like sitting on top of event streams, right, and trying to understand, okay, how frequently do I need to chunks and you know, collect those and dump maybe to some S3, and that is basically where we together trying to combine our event streams, right, into like together with our batches, right, because if somebody's sending like a big file of, I don't know, 5 million rows maybe inside, it doesn't really, on one hand, we can basically stream through the same pipeline, but if you already have the file, we do it differently, right? So we have like a separate, originally it started as a Lambda, after we changed it a different direction, but originally it's kind of like goes through the file, trying to validate it together with the schemas that we have in Igloo. We see that it's like all good, and after we have this like a data gobbler, that is named like after one big bird, to actually ingest it inside the Redshift. So essentially, it looks like it's many components, but practically it allowed us basically to start with you know, complete Snowplow, and after just change piece by piece basically without having too much trouble. So I think we were like operational from, I don't know, maybe first couple of weeks we were like just trying to understand how Snowplow gonna work. We kind of like, okay, it's working, and after we got it running and step by step started to change what had like as a bottleneck for us. So it was pretty working good for us. Yes? Sorry? Yeah. Correct, yeah. So basically, because in the title of this talk, we're also saying like 2 engineers, but essentially it's like very few people. That's how you can read it. We don't want to create schemas for our people, our consumers, right? So if on one hand you can, define maybe like in Python code or like write some custom validators, that's something that engineer can do. But if you would like to scale to have like many people to create schemas on their own, that doesn't work, right? And in this case, Igloo is kind of open source products that allow you with some not very super beautiful Swagger interface, define what field you would like to have inside of the schema. Mainly, there is like a JSON schema, and you can say, okay, I would like to have product ID. Product ID is integer. I would like to have something else, blah, 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 right? So essentially, person can be like in clicky fashion, be able to define the schemas, right? And after, based on those schemas, we can do validate of all the data. We can create the tables inside of the Redshift. So essentially, we're offloading all of this work from us, like creating like all those tables to somebody who doesn't maybe even know computer science or doesn't have a computer science degree, can just like click it, try it out. We also have like quite a bit of reporting like to Slack, right, to give you information that, okay, it's failing because your schema is wrong, there's something else basically, so we're just offloading to the people to do that. And Igloo is open source solution basically for JSON schema management. Does it help? Any other questions on this slide? Yeah, so on one hand, here you're like till that moment, right, you're receiving like a bunch of files, right? And it might be that we have like even multiple concurrent files, right? So essentially, data gobbler on one hand is like trying to not to write to the same table like a multiple updates, because otherwise you're locking and you having some problems with Redshift. And on the other hand is basically making like all beautiful and scalable. So it's kind of like this big bird that consumes like all the data beforehand and after putting inside of Redshift. So like nesting it with a nice tables. Yeah? Okay. So much, not so much of Athena, so I'm gonna go a bit ahead and explain all of that. And just to show a couple of products that we have internally. So for instance, I don't know, if you're running like product teams, right, and you would like to understand if features are helpful or not, we have something that is used to be called shiny significance. Now it's, I don't know, Euler significance or whatever else with new versions. But the idea is there is that, we have this like lots of data inside of Redshift, right? And based on this data, we have some applications that can, oops, sorry for clicking around, can run some significance basically to understand what is the p-value, how significant those like tests that you're running. Another product that we called is a changelog. If you like a big organization and everybody is like really moving fast, right? Sometimes people forget to communicate, meaning like, I don't know, I'm deploying some amazing feature and after next day people is like, hey, but why my thing is broken basically? And you can always, like complain about, AI and about robots, or you can just like try to solve the problem. And the way how we solve this problem is basically said, if people forget about sending or communicating to each other, what if we try to build a system that make it easier, right? And essentially, that's what changelog is called, right? Imagine that you building something and deploying within one team, right? We allow you to send like the small changelog messages saying like, okay, I'm, I don't know, like product or website team, I'm deploying like a new version of website, my changes is blah, 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 right? And the moment when they deploy it, that CI is kind of like going through, right? Any other team afterwards can receive a message like this saying like, I don't know what is helpful here. For instance, we started like some A/B tests about position compensation. And potentially, all of your users, they can also subscribe for different type of events, saying like, I don't know, we're dropping products. What if number of products more than like blah, basically get it automatically. So it allows us to receive quite big amount of information without like overloading, because you can subscribe for specific type of events. Yeah, and it's pretty cool. At least I like it. Maybe nobody else, but I enjoy it anyway. Okay. And as you already found, we don't really like to redo the same boring things, so we're trying to also like help and educate like other people. So with queries, it's kind of the same, right? If you have like a big BI department, it might be helpful that you ask questions, and after those people being smart and I don't know, fast, hopefully they answer your questions, right? But the problems are, if you have like many questions, and hopefully if those people answering your questions, you're gonna have like more of those, you're bottlenecking on those team, right? So essentially it's getting like slower and slower, and you're asking like less and less questions. So what we introduced is something called like data heroes, and the idea is to be like brave as this girl, and essentially we have, we had some kind of like onboarding for all those people to explain what is like SQL, how they can query like our data, what kind of data we are having, and also get feedback from there. There you can also see somewhere in the corner Stefan with like a different haircut, so it's still the same person as in the room. And we had like I think 4 or 5 weeks of onboarding in the beginning, so everybody can understand what is SQL, even if people are totally different departments. We have some people from HR or like doing some performance marketing, but at the end of the day, if you have seen those like 60 people, a bunch of them basically learned SQL together with us basically. And now instead of like, asking like, hey person, you know how to do queries, like can you answer my questions? In many cases, they are like helping each other, right? And I think it's pretty exciting. Yes, so you have seen that on one hand, we started with like big amount of data, right? We also introduced like many users how to query this data, right? So I think at some point it might also like bring a bit of like bottlenecks because everybody is like starting to query. And if you still remember what I was saying about Redshift, right? We had like 4 nodes, right? And I mean, those like 4 nodes were big, but you didn't want to over provision it in the beginning, right? Otherwise you're paying lots of money kind of like for nothing, right? So it was more like, okay, so that's like our load, right? Maybe let's add something on top of it so we don't really bottleneck in the beginning, but it still had like limits, right? So with that, I kind of like giving my microphone to DK.
Yeah. Hi. So, as Sergei was telling, like in this part, I would like to say about how we were scaling and what is the need that arises for us to scaling. If you can see, this is a normal utilization of our Redshift node. This is for the last, yeah. This is for the last 3 weeks, which I took in the afternoon. So if you can see, like, it's like for day. Usually, like, if you notice, like, almost all of your database or everything or data warehouse, this is how the utilization should be, because it's like you won't be having anything which is running 24/7. So it will be like the user, they come and query then and there, or some of your ETL jobs that run in a particular time. So this is how it should be. But if your system looks somewhat like 70% all the time, believe me, my friend, you are doing it wrong. So it should be somewhat like this. So I mean, like, we are just starting with how normally it looks, and then wrong direction. So this is how like for a 2 hour or something, I took how the queries were running in the Redshift. So if you can see, here you have a cluster of queries running at the same time. It's maybe either any of our jobs running at the same time, or some of our biz development people or sales or finance people, they are running a report in our BI tool. So there is a lot of queries running at the same time. So that is how it looks. I mean, this is common. But what does drove us to begin the journey that we want to scale up from Redshift is mainly the seasonal queries. Yeah, every day we have seasonal queries, but they are limited. But consider the situation like end of a month or a quarter, where the salespeople or business development people, they start running their queries, like, because they have like different countries, different customers, different brands. So at the same time, everyone will run their dashboards or their reports to get the result. So that is when the problem arises. Suddenly you can see people pinging us like, okay, the query is taking longer than ever, why is it down or anything? No, it's like at the same time, all of you are running the query. So like, it has the bottleneck. The solution is either we have to scale up for that time, like we are running, as Sergei was telling, that we are running by 4 nodes, then we have to just spin it up to 8 nodes just for the particular time. And there is also the issue of like, you have downtime when you are scaling up, and again when we scale down, there is also downtime. Okay, you can say like, okay, why do you need to scale it down? Because you are getting the queries, so keep it like 8 nodes all the time, but we are paying money for nothing. Like just for for 2 or 3 hours of queries running, for many queries coming at the same time, it means like we are paying for nothing. So that's when we thought, okay, what is the other solution that we go? But even before thinking of other solutions, we thought of like, okay, is there a way in which we can fine-tune our performance with Redshift? So these are the main key performance that we were doing. The one is the column encoding. which I mean like in Redshift, each column has its own encoding. If the encoding is correct, your queries will be fast. We tried it out and really showed us some performance increase. So it's like simply how to go like Redshift has this inbuilt SQL command, analyze encoding the table name. It will show like what are the columns and what are the coding it should be, but what is the coding that you have. It will just give everything. And also like if you can see here, like the link is included. It's basically that AWS lab GitHub page. They have their simple Python utility, which will do everything. You just give the table name, it will go run, check what are the encoding. If the encoding is wrong, it will create a new table, transfer the data with the proper encoding. It will done everything for you. It will do everything for you. And yeah, it helped us improve at the time. And the second thing is, like we usually like think like, okay, even my varchar column can increase, so I will just give like 56. But obviously you will maybe needing a varchar size of 16, but you will give 52 or something, because the data may grow in the particular column. You will just leave it. But the problem arises is when you run a join query or something, the temporary query is taken and temporarily it is stored in disk. So obviously you are giving a huge load. It is not compressed at the time, so there is a huge memory there and it slows it. And like if you have used Redshift, the main thing that you have to focus is the distribution key. So you have 4 nodes. Redshift is storing the data, like how it should know like on what basis it should equally distribute the data across the nodes. If you don't say it, it's like consider a single table has like 10K records. If the distribution key you don't give it, it's like Redshift will randomly store data. So your node 1 will have like 5K data, node 2 will have 4, and the rest of the 2 other nodes will have just 500 records. So at the end, when you run the query, node 1 and node 2 will have high CPU utilization, and it will be taking a long time, and your node 3 and 4 will be like doing nothing. They will just give the result. So at the end, you have to wait a lot. And yeah, obviously, short keys. I mean, we had these 3 things, majorly these 4 things we did, and it actually helped us improve the performance-wise. But still, when the seasonal queries, everyone's query at the time, it is not of a big help. So what can we do next? So we are thinking, from the base, like what are we already using? We are using an MPP system, massively parallel processing system. So should we go to SMP? No. It's like it even worse. Like normal database, or it's like, that's what, you should always scale horizontally, not vertically. So then it's like an example, like you have like Redshift is an MPP, Hadoop is an MPP, Hive, Presto, everything is an MPP. And we are thinking like, the main reason why we thought like going for pay-per query kind of MPP is we don't have to worry about the infrastructure like how we have. Do you have to scale it up, scale it down? You don't have to worry about it. Basically, you pay for the query, you just give where is the data, you properly do the partitioning, keep it properly, you just pay for what is the data that is being scanned. So that's okay, then it seems like a good solution for us. So it's like, we can go for something like that. So the first thing in the market you can say is obviously Google's BigQuery. Like, yeah, it is scalable, it is done by, it's for enterprise data warehouse, done by Google. It supports almost all your data formats, major data formats that we used in data, like CSV, JSON, delimiter line format, Parquet, Avro, ORC, which you store it in Google Cloud and you give the path. BigQuery does it. But, and also like one thing that that caught our attention is like when you are doing the partition, especially in Google Query, you can either do the partitioning based on the data, based on the ingestion date, that like on what date you are putting the data inside the Google storage, it takes that as a partition, or you can specify other columns, which especially has to be a timestamp of date. You can't just say, consider we have a product country-wise table, and like the query obviously you are going to do is like products for a country. So your segmentation, your partition should be a country ID. But here you can't do that. So obviously you will end up paying more. So that is the one thing that we kind of found it. But still, we use Google Query because our GA stuffs are there, so still we use it. But that one thing is like what we don't like in it. So, I mean, like, this is a simple example of how a big query will run it. You just give a query, the mixer will split the query, give it to the different nodes, basically a MPP. So, you can just get it. Yeah. So, next what we thought is, okay, but yeah, Google BigQuery is good, even though only the partitioning is the problem, it is good. But the problem is like our entire infrastructure is in AWS. So, all the data is here. Should we move it again to Google Cloud and pay money for moving it from here to there and do it? No, that's not a good idea. So we thought, okay, S3 is good. I mean, S3 is reliable. No one can say like S3 is not good. So can we do something with it? And we were like, we also had used Presto. Presto is more nothing but a distributed SQL engine which can run over Hive. So we put some our JSON files, converted it to S3. I mean, Parquet files, stored it in S3, and we put up we spinned up some EMR cluster, and we pushed it, and we ran Presto over it, and we are querying it. Yeah, it was good, it was doing well, but again the problem is back to square one, infrastructure. When the seasonal queries comes up, we have to again spin up the cluster. Like if you have running like 8 nodes, we have to spin it like 8, 10, 20, whatever nodes. Then yeah, back to square one, the same problem. Season query comes, you have to spin up or you have to look about it. So what is the alternate solution? Yeah, AWS Athena. It's not Amazon Athena. Athena is nothing but it's more like a Presto as a service, you can say. AWS is giving for you. It's more like Lambda. You don't have to worry about what the infrastructure. You don't have to spin up, spin down, anything. You just tell AWS Athena create a table, more like a Hive table. Tell S3 consider AWS Athena as your Hive, and S3 as your HDFS. Similar. You tell, okay, I have a table. My data is here. I can do partitioning, and this also supports all the CSV, JSON, ORC, Avro, Parquet, all the format. And the other thing we find here is like we can do our custom partitioning. It's like with BigQuery, it is only restricted to date and timestamp. Here I can do whatever I want. I can partition with like, consider I have a column like country ID. I can do a partition with a country ID, or I have another just as a internationalization, ID, everything I can do it. So it kind of made sense because it's like a few of our queries, we know like for certain tables, we know how we are going to query it. So obviously, so when we do the partitioning, it was even faster and you even pay less. So this is how we set up with Amazon S3. So, okay, yeah, we did this. So we put already our data is in S3. So initially we kind of tried with JSON. We just want to know like how are the other services that are related to Athena work. We tried AWS Glue. Has anyone used AWS Glue? Yeah. So basically we use Glue crawler. We tell the crawler, okay, why we do is like when you keep on adding new files, you need to refresh the Hive metadata to tell the Athena, yeah, this partition we had added new files and everything. So instead we just let a Glue crawler tell it, okay, this is the path, my bucket slash blah, 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 whatever it is, and we have the files with proper partitioning and everything. So we can specify like run it every day if you want, because you know like the table will be updated only once, or the data can be uploaded like every 1 hour. You can tell it like run it every 1 hour. It's like up to you. You can schedule it like a scheduler. It will run, go, refresh everything. Then it is like it updates the data to the data catalog of AWS Glue, and the data catalog can be directly connected to Athena. So you can directly go to Athena and you can see, okay, whatever the table you created will be there. You can just query it, and you only pay for, if you do the partitioning properly, you just pay very less, and also the query will be fast because it doesn't go and read the entire data. So that thing was really good for us. So we are like, okay, then we started like, it was just more like a simple MVP. So just we practically put the data inside it, ran it, done it. So, but it is not more like a system that we can run in place. Yep. I mean, like, it's not stopped there. I will come back, but Sergei will.
Okay, so how many of you are actually querying data or do some kind of like data science things? Yeah? Okay. Were you kind of like understanding all those like Athena and like where is it going, like, and how to query that? Or not so much? Yeah? Okay. But I think like, yeah? Yeah. But like our lead is not about like a building like, I don't know, let's say Athena. Our lead about like a building, maybe machine learning for that, maybe ranking, maybe relevancy. It's not of a competitive advantage. I mean, it's nothing like that we would like to have a secret as of us. I mean, if you're gonna build like Presto, maybe, but we're building a different product, so. Any other questions? No? Yeah. 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 I wouldn't say so. I think in many cases, like our redshift was like even slower to go through this amount of data that we had. So this like a time of like a bootstrapping of the nodes, right? That Presto going to be using for computation. It doesn't feel like any longer. Like in many cases, it's even faster. So we didn't have like latency number per se because we didn't really use redshift for like OTP use case when you just like in real time like answering something. But so far, like all of our users that were able to use like any of like Athena, they were like kind of happy and like that looked exciting. So. It's a combination. So we have like some materialized parts that we kind of like see and they are like faster. But in very few cases, we really feel like, okay, let's have it like all in memory because it's gonna like shave like half of the second or something. I mean, it doesn't save us that much of energy there. So this is like way bigger bottleneck that we had there. Yeah? Awesome. I think it's awesome that we are talking, otherwise like it's kind of a bit useless. So just like example, if you would like to query this data and after all this like maybe new, I don't know, abbreviations like MPP and whatsoever, it might be like, oh no, now I need to have some like somebody who knows what is Athena and how to query it. Actually not, right? So essentially on one hand, you can still write like a normal SQL stuff, right? Additionally, maybe you would need to understand a bit of stuff from Presto specific SQL, maybe like cardinality or filtering stuff, but overall is pretty similar what you would write like in a normal SQL stuff, right? And we have like a separate, a function like for run query, but essentially what's happening like in the background, right? AWS is kind of like saying, okay, I'm receiving like your query, right? I know from meta definition, right, where tables and where data and what partitions it's using, right? And it's saying at some point you like, okay, I got your query, I'm gonna execute it, right? So it's getting like execution ID, and after you query it, it takes like a bit of time because in this case we kind of like querying like a huge amount of data, and we got basically result file of 10 gigabytes because it was like pretty big request basically that we wanted to receive. So on one hand, it's kind of fine because we don't need to run it like on our infrastructure. We don't want to, employ like another 10 people who are going to maintain our like Hadoop cluster just for sake of Hadoop cluster. But on the other hand, you can see that, like result of it, we receive like in CSV. So I mean, it's good for some cases. If you're having, I don't know, some image information inside of vectors, maybe CSV is not really the best use case. But I will come back to that like a bit later. Here's an example how we're using this data. Use like a no index from Spotify, if you have heard about that. And we can just do like a simple, image similarity based like on those vectors. So essentially, you as a data scientist, you don't need to take care, okay, is my Hadoop cluster right now is like busy by running some daily jobs, or is there like anybody else doing something else? You're like pretty flexible because all of this infrastructure is provisioned by Amazon, right? And you can just like spin up as many queries as you would like, and it's all going to be scaled basically for you. And you can use like a normal Jupyter for actually connecting and getting results out of there. Yes, unfortunately, as you have seen, there is like CSV, and by default, results of Athena queries are going to be stored like in CSV. And you're going to be not always happy about that because, I mean, it has like Parquet, right? And you can read Parquet, and Parquet has provisioning, like, and all of those things, right? So can we somehow query the data and save result in Parquet, right? So we can faster load it with Apache Arrow. Turns out we can. It's not the most beautiful and elegant solution, unfortunately, but it does work on my machine, so I would just go for this way. So what you do is basically saying, for Athena, I would like to create a table that has like a query basically as a definition of that. And this allows basically to define this Athena or like this table in Parquet format on S3, right? And if you run it, it's kind of like saying like it's created somewhere else. And afterwards, if you're using like PyArrow, Apache Arrow and Python wrapper for that, you will be able basically with a S3 file system, right, read the data set, right, and convert it like directly to the pandas. So you don't need to, try to extract from a CSV file this like a nice like NumPy array and try to cut like opening and like closing braces. So it's like way more flexible and pretty convenient for us. Any questions about this? No? Perfect. So now I just, we got this data and we kind of like explain how data science can use this data, but there is still a bit of questions like, okay, I'm like a separate team sitting like in a separate part of the office, right? And we need to convince them basically to use our package, right? Because otherwise they can say, my data is like in database and I don't want to care about your data lake and why the hell are you talking to me? I have like so many things to do, right? So for us as a data platform was also like a bit of challenge, how to make it like the most convenient, right? And effortless basically for those people to adopt this solution. And that's where DK is like jumping in.
Yeah. So as Sergei was telling, like we had to convince other teams to follow this new data lake thing. So then it means like whatever the data they are storing in their S3, they are just storing as JSON line files mostly. They have to convert it to Parquet and then store it in certain partition and everything. So like if I come and tell, like consider like your colleague comes and tells you, yeah, hi, there is a new so-and-so fancy technology, we are implementing it. Okay, there is an extra work for you, just do it. No one is going to do it. So we think, okay, how do we convince them? So we actually we actually build a package, our homegrown package, which actually does the which uses, as he said, which uses Arrow, the Apache Arrow project, which uses that. This Python package, what it does is like you can pass the S3 file, it will convert it to Parquet, and you tell the partitioning and everything. It will go right to S3 based on the partitioning. It does the schema encoding based on the schema that you have. I mean, Parquet will have a schema encoding. So it does write the schema encoding, do the partitioning, everything, and write it to S3. And also it creates the glue crawler if it is not present there. So it's more like a plug and play. So they didn't have to do much of a work. Like we have given them a plug and play kind of solution. So like I can show the full picture. Yes. So this is how we initially thought of giving the proposed solution for the other teams. So the ST Cuckoo is the package that we made. You can ask why Cuckoo. Like as you had seen in the earlier, almost all our project we named them after birds. I don't know why the naming standard came, but still we are following. Almost all our projects are under the names of birds. And here why we use cuckoo is, the fun fact about the bird cuckoo, what it does is, it goes to other bird's nest, lays an egg there, and it just leaves it. So the other bird thinks, okay, it's my egg, so I have to hatch it properly, take care of it. Likewise, we are giving them a package, okay, take care of it. Like, not just outsourcing, it's more like, instead of them directly telling them, okay, here is the data, you take care of it, we are telling them, use this, you do the processing and give the final data. So it's kind of little outsourcing. So it's kind of, we gave it the name as Cuckoo. So back to the architecture, how it works is like, consider it is some application, like their team, like different team, they have their own application, which actually writes data, a raw file into S3. The first step is done. So now what they will do is, they will send a message to a queue, which is telling that, okay, this file is written in this place, and this belongs to this table. So this is the application. They make use of the Cuckoo package. They just write it, send it. So what happens is, this Cuckoo will read the raw file, the package, and as we said, the schema maintenance is the igloo that we told earlier. For schema management, the igloo, which kind of has a Swagger UI and everything. It goes there, it takes the schema for the so-and-so version of the particular table, it checks line by line of the JSON file, does the validation, is every file is right, yeah, it is right. So it generates the equivalent schema for Parquet, convert the Parquet file, do the partitioning, and write it to S3. So yeah, the file is ready. But how it goes into the data catalog? So still the Cuckoo package will take care of, like, okay, based on the schema, it will, like, we kind of follow the standards. So like versioning system, versioning naming, based on that we will check if there is a crawler which is already present in the glue crawler for the particular schedule table. If it is present, it just leaves it. If it is not present, then it will create a new crawler, and the crawler keeps on running on regular basis, whatever we give, and the Hive metadata is updated to Athena, and you can query it from Athena. Yeah, that's what the solution we first proposed. But even for me telling the solution, it's kind of huge and it is complicated, and no one is going to ready to take, like, whenever we say like, okay, this is this, yeah, it looks good, but no one is ready to come out of, they also have their tasks, like no one is ready to just come out and do it. So we are like, okay, can we even simplify this? Yes, we can do it. Okay, before that, I would like to add a note about the Cuckoo package. As I said, we used Apache Arrow project. Have any of you used Apache Arrow? I can get here and there. Okay, so what happens is, like, if you install the PyArrow package, it's basically they have the wheels installed in it. So you just, if you give pip install PyArrow, just install the wheels, yeah, done. But most of our, we have most of our infrastructure in Kubernetes, and we run Docker containers in Alpine image. And you know Alpine. It's like, nah. This is Marshall, I don't use these wheels. I use a different dev library, so I don't use it. Okay, fine. Let me build the entire thing in the PyArrow and install it. Even that is not supported. So it's basically you cannot install it via pip, or you can't even build the entire PyArrow package as well. That's how the issue was. Then later we kind of met the founder of the Apache Arrow project during a conference, and he told, like, yeah, the problem is there, just now we find a solution, there is a PR, go and check the PR. So it's basically like they go and change some stuff in their assembly files when they are building it. So it worked. For that we spent a lot of time trying to crack it, but finally they found a solution and they gave us. So that is one big of hell that we are facing it when we are using Alpine. So if people have used Alpine, you might have a lot of stories like this. Then we are like, okay, fine, leave that entirely. Let us go to a simpler version, which the teams, it will be even more, little bit easier for the teams to use. So we are like, okay, let us build a CloudFormation stack. They just deploy it. It almost kind of builds the solution for them. They don't have to do much of work as compared to before. And building the CloudFormation stack, it's not like a normal way. For that also we have a homegrown package. So it's basically you write a set of Python codes which does take care of doing the CloudFormation. It creates a template for you and everything. So in that, what we did is consider, okay, yes, yeah. So here the CloudFormation stack, it's more like it integrates towards our CI/CD. So when it gets deployed, it actually deploys two main things. One is a Lambda, which is a stripped version of the Cuckoo, the package. It only does the conversion. It doesn't care about the crawler or anything. It only reads from a particular, it is, what to say, it is subscribed to an SNS notification. It receives, if there is anything, converts, writes. That's all it does. It doesn't care about anything at all. Then there is this also deploys, the CloudFormation also deploys a crawler. And also we set up a notification, everything. So basically what it does is, like, when a file is written into the S3, SNS notification triggers, and it is consumed by the Lambda. It goes, reads the file, converts it, and also here we actually avoided the schema, the igloo. Why is that? Because consider because there are sometimes we kind of get thousands of files at the same time. When there is a new customer, or when they are changing some files, they will rewrite the files. So at the same time, there will be thousands of files will be there. So in the existing system, it's more like a pipeline. So it comes in the pipe, it goes, hit a single time. But with Lambda, it keeps on popping up different instances. Different Lambdas functions. So we just tried of writing the schema in keeping it inside the S3 itself, based on the naming convention. So it takes not a convention, it's more like a standard that we follow. So it goes there, it knows this schema for this table should be under here. So it reads it, takes it, converts it, and yeah. So finally it is ready with Athena, and you can query it from Athena. So you can say the basic learning from this talk should be measured like the MVP systems and solutions that is available for data warehouse and data lake as of now, and the bottlenecks that we faced with Redshift, and what are the pay-per-query kind of solutions that is available in the market. And like I hope like you guys might have get some ideas about how you can implement Athena in your stack, I suppose. So yep. So you have guys any questions? The reason one last one.
Thank you for attention. It was a pleasure having you. Are there any additional questions? We are like more than happy to answer those. We are happier than before. Are we like the the most happy ever? There is like still some feels like a bottlenecks and not the most like beautiful solutions. It also feels as they're developing it like right now as well. So I hope like I don't know in 6 months it's going to be better than now. But the questions that we was kind of like asked before, right? I would repeat it again, right? You as a company and you as engineering culture, you need to understand what are your fights you're picking up, right? Otherwise you're going to be like fighting with a new Alpine, right? Because it was not good, right? Fighting with new Apache Arrow, right? But you need to decide what is your product priority, right? And what is your like competitive advantages, right? And I think at current point of view, it allows us to understand and like query like many data points like way faster. And if we would see that something is like really super hard to avoid, we would do something different. And we did the same with Snowplow, right? When we started with like open source solution and after reinvented like 80% of Snowplow. And I think we can do the same basically with Parquet or whatever else basically. So it's pretty open for us. Yeah? Any other questions? Okay, so just in case you're interested, we also have data analyst, data engineer, machine learning position, and awesome steaks that we eat at team events. So talk to us, and if you have any feedback about all of this and you're saying that you did it like even better, just talk to us. I think we're happy to get feedback from you as well, because it's all about community, not about us being on the stage. Thank you very much.